Okay. Hi, everybody. In this lecture, we continue our work, which we have begun in the previous lecture. We are still working in nonlinear regression by using nonlinear curve fit LM formula string. Remember, I have told you that this algorithm has two settings or options, either to use nonlinear curve fit LM formula string, which we are working with now, or to use nonlinear curve fit LabVIEW. The other important thing here is, in this option, that we have to define approximately the fitting function, which could be successfully used to give accurate results. So it should be as possible closer to the real data set of the system. The inputs again are the Y data set, which represents the real measurement values. In real life, they are taken as a result of experimental work. And the other input represents the range of, or the values within a range of the input signal X. Here we have to create a synthetic data set representing the X and Y also. In order to work with this function, the size of both arrays at the input here X and at the input Y must be the same. In this example, I have selected the same expressions and values which I have used in Python, so as to get an answer which could be compared with the results which we have got with Python. This was done at lecture 1.7, remember. So this function is also multivariable. We work with two variables, x1 and x2. We have to create both of them. And x or y itself, the output, is in the form of a coefficient a multiplied by numpy exponent of the product b by x1 plus another coefficient c multiplied by numpy sine of the product d x2. So what we have here, we have four coefficients, d and c and b and a. These coefficients are to be found by the algorithm. To work with this function, we need to create an array representing x1 and another array representing x2. x1 here is as an array in pi len space in the range of 0 to 5 with 100 samples. These values were taken and used by us in Python. And x2 also is given as numpy len space in the range of 0 to 10 with the same number of samples multiplied by npi exponent of half x1. So we have at first to realize x1, to create x1, we have to create x2, we have to combine x1 and x2 and fit them to the input of the function here. After that, we should create the function representing the measurement, which is given in this form here. And after that, we can run the program and see the results and the goodness of the fit as the output of the algorithm. So we use in LabVIEW ramp pattern VI to generate an array within a given range between 0 and 5, as it is here in Python. And I have selected the number of samples 100. I think it is the same as in Python. So this is the output and is shown through the indicator X1 on the front panel. Now, in order to create X2, we need to use X1 and multiply it by half and find its exponent. So this is the exponent function. It is the exponent of the product half multiplied by x1. This will be multiplied by x2 by n-pi length space between 0 and 5 and 10 with 100 samples. So here it is the range between 0 and 5. Now, to create x2, it is in the range between 0 and 10 with the same number of samples here as here. And now we got this component. This component will be multiplied by the exponential output here, and this gives you x2. Now we use x2 and we use x1 through a build array. We can concatenate both, and here we shall have a one-dimensional array which feeds the x input. Here I have shown you also that we can create an array of both arrays, x1 and x2. Both are input to a build array, and as output we get two-dimensional array. This two-dimensional array also could be reshaped using 200 values instead of 100, because this is 100 and this is 100, and both arrays will be included at the output one after the other. So the size of the concatenated array will be 200. So I have put here 200 as a size, and at the output here we shall get x, big X here. It is the same as the X which we get at the build array when it is concatenated. So the value here or the value here could be input to the X input of the function. Now we have created the synthetic array values which represents the variables x1 and x2. Now we shall use x1 expression and x2 expression to find the y value. In real life, we shall also, of course, we shall create this expression as a function and add a component of noise to it so as to represent it as if it is a real measurement. So at first here, I have created an array of values between 0 and 5. Here I have taken 200 samples because the samples of y must be equal to samples of x. Here it was 200 in x, so again here now it will be 200, so it is 200 now. Now I have multiplied x1 by half, and I have taken its exponent. This is x1 multiplied by half. Their exponent is taken, and this exponent now will be multiplied by n-pi len space between 0 and 10. Here it is created another array between 0 and 10 with 200 samples. This is the output, which is multiplied by the value which we have got as the output of the exponent. Now, this value will be multiplied by the sign of the product d multiplied by x2. D here is given .7 as it is in Python. We multiplied the output by .7 and we have taken its sign output here, and the output of the sign will be multiplied by the coefficient C, which is 1.8. So now we have, this is the component, the second component. Here the first component, which is x1 multiplied by half, taking its exponent and multiplying by a, which is 2.5. And now we have both components, which represent the useful signal y. We add to the useful signal y a noise component here. Now you know how I got it. And the output now will be fed to our function. Now we go to the formula which we will use. We are going to use exactly the same expression because we know it in advance. A0, this is the first coefficient, multiplied by exponent of A1 multiplied by x. This is the first term. And this is the second term, A2 multiplied by sine A3 multiplied by x. So here we have A3, A2, A1, A0, 4 coefficients. Here they are fixed exactly in the same sequence, A0, A1, A2, A3. The variable x is shown here. This x now represents the concatenated x, of course. And with this, we have finished with the input side of this function algorithm. We have to define the initial coefficient values. They are given here as 3 minus 1, 2, 2. Of course, I have selected them at first randomly, and then I have tuned them to get the better possible R-square coefficient. Now, in order to test the function and to can manipulate it successfully, at first I have created the synthetic data set as an x and the y bundled together, and the other value with the same x and the best fit as the output of the system. Both of them are now joined together as an array, and this array is plotted using the XY graph. So the XY graph here includes two data sets. The data set with points, which represents the synthetic data set with noise, and the data set at the output, which represents the optimized values or the best fit values of the regression function. So each point at this curve represents a best fit value. As you see, it has a sinusoidal or wavy component because we have here this sine component here. Now, if we go back, also, I have taken the output, which is the best fit y values, compared it with the input y value at the system here, so as to find the goodness of the fitting, and so that I can manipulate the values of the initial coefficients or change some things which lead to better performance. The output here is clear. We judge about the performance by the value of R or the value of the mean square error or root mean square error. These values are practically derived from one each other. The smaller the value of the mean square error, the better, of course, the fitting, and the closer R to the value of 1 means we have a better fitting. So if we go back now and run the program, I will run it now, we shall see nothing has changed because the settings are already given. And if we consider the value of the R square, it is 0.337, and the mean square error 1.5. Really, the mean square error is a very good indicator, and it is very small and is close enough to 0, which shows that this result is acceptable. The R value here is comparatively small, and it is not very close to the 1 as should be. I really kept it here exactly so that to compare the results which we have obtained here with the results which we obtained when using Python in the previous lecture. When we used Python, the R square was equal to 0.38, here 0.33. They are very close. And also the mean square error 1.5. Here it is also 1.5. So the results practically the same. Really, we can improve the results here because we see the values and we see here the curve. We can somehow change the performance by changing some of the parameters of the model itself here, because we have this freedom to do it here, or to change some of the coefficients of the initial array. Really, I have tried to change, for example, some of the coefficients here. Let me say from 2 to 4, I have given you here the third one to 4. And now if we go and look at the coefficients here, after I run it, it doesn't change any way. It's exactly the same, which means that the algorithm is working exactly, and this is the best thing it can give you. If I write here instead of 2, let me write 6, for example, and I run it again, and look here, what has changed really is the fourth position here, which means also there is no serious effect and there is no serious change. So these coefficients which are selected as initial values are really very relevant and very accurate, and give the accurate result which agrees with the result which we have got with Python. But also, really, the R and MSE values could be improved here by using or changing the level noise, the level of the noise. In real life, of course, if there is a high level of noise, you have to decrease it. Here in our case, for example, the noise here is selected 0.05. The set value, usually the default value is 1. If I write it here, let me say 0.1. I doubled the level, and if I go back and run the program again, there is a slight change. It increases here at the third position, but it is not that one. Let me increase the noise more. I think that the error will be higher. Let me say it is 1, for example. Now it is 0.325. If I run it now, it will be smaller. As you see, 0.205. The level of the noise increased, the accuracy of the system decreased, and really it is now different than the result which we have got before by using Python. Now, if we go to the system here, the model which we have introduced, I have introduced the coefficient A here, which is found by our algorithm as 2.9. The given value by the model was 2.5, but the predicted value is 2.9. If I take it, for example, higher than this value, and I put it here instead of 2.55, for example, and I go back and run the, now notice 0.2. Now if I run it, now it will be with a higher, now it is 0.365. It is closer to Python. If I increase it more from 5, let me say to 8, maybe, and now I run it, so it is now 0.48, which is better than we have got with Python. And you see here, the curve itself is going practically in the middle way between the mean value, which is around 0 here, as we did, as we expected. Here is the 0 level, and the mean value here is about 0 also. So as you see, the function works fine. To summarize all these things, the most important thing here is to create a model function which is relative to the data set and copes with its trend. And then you can manipulate the coefficients through the initial values which you give to the system here, to the algorithm. And after running the program, you can judge about the fitting results and accuracy by checking the mean square error value or the R squared value. And as you see, you have large space of activities where you can manipulate and drive the performance of the system in the direction you like. Okay, we finished with this example. Let us go to another example. File, exit, don't save. I want to keep it. I have prepared for you also another example, which is 400 6 example. Continue. Okay, let's go to the block diagram and see what do we have here. Now we are still working with curve fitting and fitting for nonlinear functions. But we are not using now the same algorithm which we have used before. In LabVIEW, we have this function also, which can carry out fitting of multivariable nonlinear functions. Where it exists, I can show you. You can go to mathematics, to fittings here, and here you can see curve fit. This virtue, it opens directly, and as you see here, it has many options which you can use. You can use directly a linear fit, or quadratic fit, or polynomial fit. Also, you can use nonlinear fit with a given number of terms. You have to check this input nonlinear now, and now you can use an input x, which represents the concatenated x of the values of x's which you have, if they are 1 or 2 or 3 values, and you have now already coefficients given as A, B, and C, but you can increase them to C and D and F, and directly, when you run the program, you can get here the output values, or the best fit values of A and B and C and D and E, as you like. So we shall work with this option, with this algorithm, through an example and show you how it works. Okay, so we go back to our, now I cancel this one and I keep the original VI to show you the connections. Here, this original VI, or it is called Express VI in LabVIEW. This Express VI has two important inputs. One of them called signals, the other one called locations. Of course, you have not to learn by heart what does it mean. If you have forgotten, you can go to the help and see. Yes, and you can see the curve fitting Express VI, block diagram outputs, block diagram inputs. Here the inputs, for example, here he shows you that the input signals specifies the observed values of the dependent variable. So this is the measurement. Locations specifies the values of the independent variables. This represents the x values. So when we go back, now this is not necessary for us. This signal's input must be fed by the values which represent y, or the measurement values. The other, which is locations, is the x values, which represents the concatenated values of x. I have taken two x's, x1 and x2. And as I remember, I also have taken the same values which I used in the previous example, which were used by Python also, in order to have an idea about the performance and to compare performance in the three cases. Well, a different thing here in this example, the generation of the synthetic array, which represents x1 and x2, now is taken differently, but I did not use the ramp by sample function. I have used another simple as you see, a block diagram here, where you define the minimum value of X, the maximum value of X, the number of samples which you want, and again, through this small for loop value, you get the output here. As we did, if this is X, in LabVIEW, I have called it M0, sorry, in Python. This is X value of the output is multiplied by half, and the exponent of this value is taken. So we get now what we have called Y2. So we have here X2. So we have here X1, and here we have X2, but here they have the same range between, let me say, 0 and maybe, as I remember, the maximum value, 7, for example, between 0 and 7. But indeed, in the previous lecture, we used another limit for X. It was between 0 and 10, as you remember, not 0 and 7. If you go here, I see this is the minimum, not interesting. The maximum, it is taken as 10. So the difference agrees here between 0 and 10, there between 0 and 7. It must be, I think, between 0 and 14 then. We shall see now. Okay, so what do we have? Now, again, this is just to show you. So now we have generated an array, and this array, as you see here, is X. And it is now fed to a build array, which is concatenated with this input, so that to get at the output the concatenated Y, the useful signal Y without a noise. So this is X, and this input must represent X2. X2 is equal to X, here is the output, here it is X multiplied by half, and then we have taken the exponent of it, as you see, and this is multiplied by the output here, which is length space between 0 and 10, here 0 and 10. This is the length space between 0 and 10 array. As you see, it is multiplied by the X1 multiplied by the exponent value here. This gives you the value of X2. Let me write here X2. And here X1. And now we have concatenated both. We have got X, and this X will be fed to the input. Now we have to create the real life or a data set which resembles the real life values which we get when we carry out any experiment. So as you remember in the previous example, I have taken the value of X, multiply it by minus 0.5, and I found its exponent, and the output is multiplied by 2.5. Then I multiplied the coefficient 1 and 8 by the sign of the coefficient 0.7 with X, and I added both together to get Y. And this Y now will be added to a noise which is generated by continuous random VI. So this is the continuous random VI is added to the useful signal Y, and the output now is fed to the input of the curve fitting signals. So now we have the input. Okay. Here we have not to give an estimation of the coefficients. And at the output here, as you see, you have an output here as a cluster here, best fit. This cluster, as you see here, gives you an array which represents the best fit here as the output. And this is why at the input, I compared them using the goodness function to get the value of the R or the value of the mean square error. If I want to see to find the best values of the coefficients, really they are existing inside the function here. As you see, I showed you before, they should be shown here, A, B, C, D. And you do not need to do what I have done here, but I have done it for you. So this cluster again, as here indexed, and I have got as the output this array. This array represents the values of the coefficients, which are the best fit values when we run the program. So you can have it either from the inside of the program, the algorithm, or you can have it as the output on your own. Okay, one more interesting thing here. As you see here, I have a formula node in LabVIEW. It is included within a for loop to get as the output an array. This expression here, which is used, exactly the same as the expression which we fed to the input here, except that the coefficients which I included here are those coefficients which I obtained when using LabVIEW. So the array which is at the output here exactly represents the predicted array values in Python. I'm sorry, in Python. Now I have got this output here with the input X and the input X with the output which is feeding the system here to compare between the two data sets. This is one thing important. And again, to make use of the predicted values to feed them to the goodness function here, and to compare the results when using Python and when using LabVIEW, but in this case, by using the curve fitting, express curve fitting, not by using curve fitting LM. Okay, so I think now everything has been explained to you. If we run the program now, we shall see, let us go to the front panel. Now, if we run the program, here what we have. Concerning the goodness of the function, the root mean square and the mean square, as you see here, they are about 9, about 8. You square it, it will be 64 or 62. This is the output of the program. And the R value is, as you see, 0.345. Remember, in the previous example, it was about the same value, very near to it, very close to it. And in Python, it was about 0.38. And the R squared value now here is about 0.245, which is not that good, but it is acceptable, and also it is comparable with the value which we have got in the Python. Here I have summarized also the values again. These are the predicted coefficient values by this program. These are the values which were used by Python. And these are the values which were predicted by Python. So here, instead of 2.2, here we have 2.5. So our prediction in this case is better for this coefficient than Python. It is closer to the true value. Here minus 0.38, here minus 0.5, here 6. Practically, here also we are closer to the real value, to the true value. Here, Python is closer a little bit. And the fourth coefficient practically is the same as we have got here. So, generally speaking, the values of the coefficients which we get by using this function is very close to the values which we get in Python and which we have got in the previous example, and they are very acceptable. Yes. The curve itself, as you see here, this is the fitting curve by using the function, the express function, and this is the fitting function when we used the curve fit in the previous lecture or in Python. This is in Python. So it has a wavy character similar to that which we have seen before because we have a sinusoidal component. I think that this discussion has given you a detailed information on how to design and how to work with LabVIEW using the curve fitting of nonlinear multivariable functions, either by using the express curve fitting or by using the curve fitting with formula. What we have then to do more? If we go back to the previous lecture, to the previous example, let me go out of this example and go back to my example. It was here, I think. Yes. So as you see here, this function, now we have selected the option nonlinear curve fit LM formula string. We added a formula string here, which is close or the same to the real dataset trend. This function also could be used by using nonlinear curve fit LM. If you select this option, you will get, of course, an error here. There will be another connections. And there you have to draw or to plot the model function alone as a sub-virtual instrument. And this sub-virtual instrument will be called by this caller function or algorithm, and the algorithm then will be implemented. How to do that? This will take also one lecture of time. I shall explain to you how to work with it within maybe 2 to 3 to 4 examples. This will be in the coming lecture. Until then, I wish you the best and see you again. Goodbye.